In 1887, Heinrich Hertz was knocking electrons off metal sheets using light. Since higher amplitudes mean more energy when it comes to mechanical waves, he figured he could transfer more energy to the electrons he knocked off just by turning up the amplitude, or the brightness, of his light. But he was wrong. No one could explain why, until Einstein came along. That's what's up next on PS100. You can measure the energy of sound waves and other mechanical waves by measuring their amplitude. More amplitude in a sound wave, which we hear as loudness, equals more energy. And more amplitude in a light wave, which we see as brightness, also equals more energy. So if you're transferring energy from light to an electron to make it jump off of a metal sheet, it seems like increasing a light wave's amplitude would transfer more energy into those electrons. But as Hertz observed, that's not what happens. You can crank up a light's amplitude as high as you want, and the ejected electrons aren't going to get any more energetic. So, Hertz tried changing the light wave's frequency, which we perceive as color in the visible spectrum. When the frequency is too low, no electrons are ejected. And he discovered that high-frequency light waves gave the ejected electrons more energy. That left him scratching his head, and no one had any idea what was going on until Einstein came along. Einstein said light transfers energy in mass-free bundles called photons. And he explained that each photon's energy depends on the light wave's frequency. The higher the frequency, the greater the photon's energy. So while amplitude does determine the total energy of a light wave, frequency determines the individual energy of each photon. As it turns out, when Hertz increased the energy transferred by increasing the amplitude, he was adding to the total energy by shooting more photons. But since those photons carried the same amount of energy they did before he turned up the amplitude, the amount of energy they could transfer to each electron didn't change. When he increased the frequency of the light wave, on the other hand, each photon had more energy to transfer, so the electrons left the metal more energized. This has some fun implications when you're shooting bigger things with photons. Like planets. Let's say you've entered a planet-destroying competition, and whoever destroys the most planets in an hour wins. The competition's rules say all death lasers have to shoot visible light with the same number of photons, and the laws of physics say all light has to travel at the same speed. What can you do to get an edge on the competition? Well, if your opponent is shooting a red laser, I'd recommend using a blue laser. Even though the speed and quantity of your photons are the same, your blue laser photons will have more energy than the red laser photons used by your competition. So it'll take fewer photons and less time to toast planets, which is great for you, and not so great for whatever innocent and potentially cuddly creatures stand between you and your evil championship. That's it for this episode, but you'll find more science and research opportunities for BYU undergrads in the description below.